So today we're happy to have George Lusztig from MIT and the IAS as our speaker. The title of his talk is Geometric Satake Equivalence, a Historical Survey.
Okay, so this talk will be has some component will be history, but it will more like prehistory because it's stuff. I talk about older stuff, and so. Well, anyway, geometric Satake equivalence, it's something we started with Satake isomorphism, which was some statement about spherical functions for periodic group, which I will see later, and this has become something much stronger, and nowadays it is something which is used in quite extensively in representation theory. For example, I've seen some lecture by Scholz where this geometric Satake equivalence, it's actually really part of the proof of some part of Langlands conjecture. But anyway, I wanted to say how this theory started, basically. So I will start with some references. So there are four. So this one paper which I wrote, well, about 1983, and I think I will most of it, what I will say will be from that paper, and then there are some later papers were categorified, and this is Ginsburg in 95, Mirkovic, Vilonen, and Beresov-Dimfeld. Beresov-Dimfeld has no year attached to it. No, it is in a preprint, so it's not in archives. I don't know yet. And Ginsburg is actually 1990. He did a paper in 1990, but apparently archive didn't exist at that time, so he put it in archive later. So now I will. So can you read what I write here? What is written here?
Yeah.
Okay. So I'm afraid I have to start with a lot of notation. So let's see. So G will be simply connected, almost simple, over algebraic closed, and has a fixed spinning. And G star is a Langlands dual group, and W0 a Bal group of either G or G star, and X is lattice of weights, X plus are the dominant weights, and then for semi-linear product of W0 and X, that is the affine Bal group, actually a little bit extended sometimes, but it's affine Bal group of G star, actually, and it has a length function, and then you can look at the double cosets of W respect to this finite W0, and they're indexed by these dominant weights. And for each such double coset, you look at element of maximal length and element of minimal length, so capital MX and little UX. And then for us, it will be important to look at the affine Hecke algebra. So the affine Hecke algebra is denoted by H. We will take it over rational function in one variable. And it has two bases, so one is the obvious basis, TW, and one is not so obvious basis, which is defined in our paper with Kazdan, 39. And the two bases are related to each other by a formula. Well, this CW is a combination of PY, and the coefficients are some polynomials depending on Y and W. And the sum is a finite sum, actually. And then we will normalize the CW in some time. so it's written here. So you first define, consider this Poincare polynomial of W0, sum of Q2 length. Then you have the, well, this is a notation which I will use. It's a number of positive roots, or it's a degree of this polynomial. And rho is a sum. This rho will be used later, maybe the second part of the lecture. And then we also have to use the this element in the sum over TW over the finite bar group. It's called S. And then when X is in when you have this W, it is longest element, a double coset. Then this element CMX will be renormalized by, you divide by this Poincare polynomial and times this power of Q. Okay, and this will be the main, the things are mainly interested. Now there's also some geometry which I will mention, but it will not play a big role. I think in my lecture I will mainly talk about this algebra part. So the geometry is that if X is a dominant weight, you can look at affine Grassmannian of G star, and there's some orbits of this group, G star of epsilon. The orbits are parameterized again by these dominant weights, and the orbit closure are denoted like this, OX bar. And for each of these orbit closure, there is a corresponding simple Pebble sheaf on OX bar, which I will mention a little bit slightly later. And the other notation that I will need is that for a dominant weight, Vx is a Weil module of G corresponding to X. And if you have two dominant weights, then My of Vx is a multiplicity of this weight in the Weil module. Okay, so now I want, I'm sorry, this were a lot of notations, but now I will use them to state some results from my paper of 1983. So one result is that this, so again, this multiplicity of a weight in the Weil module is actually equal to this polynomial. So this was a polynomial which expresses the C basis in terms of a T basis. So these two are, and you have to evaluate at one. So here the surprising thing is that this polynomial is defined in terms of this dual group, and these things are defined in terms of the group itself. So this G and this in terms of G star. So there's some connection between G and G star. And okay, so then the second statement is that, well, the gamma X, I recall this the same as CMX renormalized. So if you take gamma X and multiply by gamma Y, there is a combination of gamma Z with integer coefficient. And there's no reason, it's not obvious why this should be integers. In principle, this could be polynomials in Q or something, or even rational functions. No, the fact that is anyway. So they're integer. This statement. By the way, this statement is called by Bergson-Dimfeld is called the miraculous lemma. So it's very it's quite surprising. But then there is a more precise statement which says that this coefficient, these integers are actually can be expressed in terms of multiplicity of this. Of course, here you assume that you have a complex numbers, multiplicity of a Weyl module in a tensor product of two other Weyl modules. So this again relates G and G star, because this multiplicity is something defined as of G, and these coefficients they are defined using G star. So another property is that, which is proved in this paper, is that this as a vector space, this Vx, this Weyl module, so the irreducible representation of G, as a vector space isomorphic to the total intersection cohomology of this affine Schubert variety, Grassmannian. So okay, so now I will say something about the proof, but before doing that, I will just say about the developments after this paper. So so actually, when I started this writing this paper, I wanted to prove the number one. The other thing, they just came out as side products, but I really wanted to prove number one. And the reason is that I had two reasons why this should be true. So before having a proof, I knew why it should be true. So one of them, which I will discuss a little bit later in a little more detail, is that if for groups in characteristic P, if P is large enough, there was a conjectured character formula for rational representations of G, the G is in characteristic P. So this character formula expressed some irreducible representations, modular representation in terms of Weyl modules in a Grothendieck group, and the formula was involved polynomials of this form, but maybe for more general elements in affine Weyl group. So this was a formula which was it was the same type as something which I collected with Kazhdan for finite dimensions, for Lie algebra, simple Lie algebras, classic 0. In any case, so this formula, this conjecture was there, and I wanted to, well, I was interested to find evidence for it, and it turned out that if this highest weight is divisible by P, then this irreducible representation, its character is known, because the representation is just Frobenius twist of some of the Weyl module. And so in that case, the formula expresses something known in terms of something involving these polynomials. And if you analyze, so you get some identity, and if you analyze the identity, you find that this formula is true. So in some cases, this formula was a consequence of this conjectural character modularizations, and then actually, in order to so for me, finding a proof of the formula was something which provided support for the conjecture. So this was one motivation, but there was a second motivation, was that in type A, I had a proof of this formula actually. That was before, that was the 1981. Because I was studying wanted to see what is the intersection cohomology of unipotent class, closure of unipotent class in GLN. So I showed that this closure locally looks like an affine Schubert variety, and then I could compute the. In that case, I could compute this intersection cohomology. So, and these polynomials which appear turn out to be some classical polynomials which appear in the character table of GLN FQ. They're called green forks polynomials. So those polynomials compute exactly these things in GLN. And for those polynomials, it is known that it was known that the value at 1 is a multiplicity of a weight. That's something in classical result in McDonald's book. So it was known in that case. So I had these two motivations. Now this property 2, let's say.
Can you scroll up? Thank you.
Yeah. This property 2, the fact that this product of gamma is an integer combination of gamma, is equivalent to product that this convolution of the simple perverse sheaves on Affine-Grassmannian, which a priori it's only a direct sum of perverse sheaf with shifts. It actually has no shifts. So a convolution of the perverse sheaf is again a perverse sheaf. And therefore this Satake category, which has been defined in other lectures in this seminar, is monoidal. So that's why Dr. Drimfeld was interested in this, because anyway, so this makes Satake category monoidal. So that's the starting point of geometric Satake equivalence. Now, but these 2 and 3 are basically the same as what Satake equivalence is, but in the decategorified form. And now, but what actually the categorified statement it's very important, and it's something which I was not able to prove. And it appeared in this paper which I mentioned before, Ginsburg and Mirkovic-Vilonen. Now, something about history of this thing, because this is the historical talk. So when I did this paper in 1983, I really wasn't interested in well, I knew that this thing can be expressed, means something for perverse sheaf, but I wasn't interested in improving this categorical equivalence. I thought that I stopped at what I did. And I didn't know much about tensor categories either. But actually in 1988, it's interesting, I was at the institute. I was at the same institute but I was not remote at the time, I was really there. And then I knew I heard something about tensor categories and this Tanaka duality, and then it occurred to me that that what I proved is should provide construction of a quantum group, but I saw that I'm not able to prove commutativity constraint. So I had no idea how to prove commutativity constraint, and then I abandoned this thing. By the way, this property 4, which is here, is something which suggests what is the FiberFunctor. If you want to go from to connect these representations with perverse sheaf, well, you have to take this total cohomology of this OX bar, intersection cohomology, and that should be the FiberFunctor to representation of some group. So this FiberFunctor was implicit in this paper, but these later papers, they rediscovered it. I don't think they've seen that in my paper because they don't mention. But anyway, so my paper contained almost everything we need except for its commutativity constraint, which I had no idea how to prove. And so it turns
George,
out that—
can I ask briefly? Sorry.
Yes.
You just said quantum group. Was that intentional, or did you mean?
No. I misspoke. No.
Okay.
Did I say quantum? I didn't. Not quantum. No, I didn't. No, there's no quantum group here. Sorry. Okay. Yeah, but there's also some strange things happen. So Ginsburg paper, he has a commutativity constraint, but it turns out that is not quite correct. So when I heard the lecture by Ginsburg, I think it was at MIT around 1995, I think something around that year. Bellinson was also there, was sitting next to me, and he said that this commutativity is not correct. I was very impressed that he could see so quickly. But then this was correct in Milkovich below, and it is correct, and is based on some work of Bellinson and Drinfeld using some fusion. And there is another proof of commutativity constraint by Xin-Wen Zhu. I think 2016 is on arXiv, I think. So, and it is based on some paper which is with Ji-Wei Yun. So this proof is without fusion. Okay, and I should also say that Milkovich, Vilonen, they also consider coefficients mod P, so which is even more interesting. Okay, so one other thing. So it's now also part of this. So now, actually, I want to mention some part of a proof of my 83 paper is presenting this element gamma x as something as a formula for it, which is very similar to Wahl character formula, and this is what makes possible comparison between this gamma x and some representation cards of a group. And so more precisely, if you take this, oops, let's see. I already defined this S, which is sum of TW, and you also have some analogous alternating sum of TWs in algebra. And then you can define for every dominant weight, you can define Jx plus rho, an element in Hecke algebra, which is this basic that is just a standard basis element, but you multiply it on the left with this alternating sum and on the right with the symmetric sum. And then the theory of my paper is that this gamma x, this thing which is a thing of most interest to us, is a unique solution of this equation, Jx plus rho equals J rho times gamma x. But gamma x is required to be in SHS, in this spherical part of Hecke algebra. So in some sense, this thing is a quotient of this thing by this thing, and that looks very much like Wahl character formula. and also map from H to J rho times H is isomorphism from here to here. And in fact, all the results in my paper are deduced from this, and that's the most difficult part. And I should say that this this theorem has been also categorified by Bezrukavnikov, Gaizgori, I think this is Mirkovic, Risch, and right there, in terms of Ivahori-Whittaker sheaves, which there were some talks in the seminar. So those Ivahori-Whittaker sheaves, they are, if they categorify them, they are exactly what is written here, except that this doesn't indicate at all the definition of what this thing should be. Now I should also mention one other thing, that I think it's that there's a different proof of this property 1, 2, 3 by Knopp in 2005, which actually I didn't see until this morning. It's very strange. So I find it, but there's different proof like 20 years later, but it has the advantage that applies also for Hecke algebra with unequal parameters. So in that sense, it's a different proof. It's simpler, but it doesn't contain this this J element, so it couldn't be cut. So it wouldn't have led to this kind of categorification. I think maybe I should stop here. Is that the time to stop?
Yes, great. Let's take a 5-minute break here.
Yeah.
Maybe we can start back up.
Okay, time to start.
Yes.
Yeah. Okay. Okay. So next thing I want to explain. So this is something which is not in my paper. So that's something which I understood more recently. Is how this what I talked before is related to the J ring. So I want to recall what is the J ring. So if you, in Hecke algebra, if you multiply this base element, CW prime, you get some structure constants, H, W, W prime, W prime. And one thing you can prove is that the largest power of, so they always of some fit to some fixed power plus lower terms. And the fixed power is length of this longest element in var group. This is something which I proved in the paper on cell snap and var group. So these coefficients are always like that. And then it makes sense to look at the leading term. So this coefficient is some integer times this largest power of b plus lower powers. And then you can redefine the product in H. You define a new algebra which doesn't involve Q or V or anything like that. Or by the way, B is Q to 1/2 here. So this algebra, it doesn't involve indeterminate. So, but has say the basis is indexed by again by alpha var group. The product of two base elements is this integer. Integer appears here, and then you can you can prove that this associative and gives a ring, and then you can consider the subspace of this J, which is spanned by T index, its longest elements in the double cosets, and that will be a subring, and in fact it's commutative. And the claim is that if you take this gamma, take the spherical part of the Hecke algebra, but take coefficients without involving Q, rational numbers, without involving this indeterminate. So just a vector space of rational numbers spanned by gamma x. Then it is this ring is isomorphic to this J star, just by obvious thing. So which means that this spherical Hecke algebra is actually isomorphic to part of this J ring. and in this case, there's no problem to know that well, in this case, this structure constant are integer by definition. There's no power of q. And in fact, this statement also holds for unequal parameters, any unequal parameters, to complete general, because this J ring can be defined, but is not known to be associative. But this part of the J ring will be associative, and this is still true. So this thing can be explained like this. And by the way, this Satake category, which is built out of this, is also equivalent to some category of perverse sheaf we defined it as of J star, and it's also true as a monoidal thing. Okay, that's one thing. Now I want to go to some different thing. So I want to look at some unequal parameter, but of a special type which appear from folding. So I assume that G is simply laced, and for simplicity I exclude A to N, and I take some automorphism of G which preserve the pinning, and this induces an automorphism of G star, and I can take fixed points of these various objects that we have W0x, Wx plus, and I get these other objects. And these fixed points, W sigma, is again an affine bar group, maybe extended. And it has a weight function. So it's not a length function, but a weight function. It's a restriction of the length function of W. So, but with respect to this weight function, we can define again affine Hecke algebra, but it has unequal parameters depending, which involve this weight. And this has a standard basis, and this has this other basis, which is similar to what we talked about before. And this is a combination of this basis, combination of that basis with coefficients, again polynomials, but it depends on the weight function. And then there is something like Poincare polynomial, but involving this weight function. And then you can again modify, you can again take this gamma x. So it's renormalize this element as before, but you using this weight, everything involves a weight function. And then there are the following two statements you can make, similar to what happened in the 83 paper. But now the group that you have to consider is not G, but is not a fixed point set of sigma on G, but is something more subtle. You have to take a fixed point set of sigma on a dual group, then identity component, and then dual again. So this group is again simply connected, and it has a var group, this fixed point set of sigma, and it has its weight lattice of this is the same as x sigma, and dominant weights are same as x plus sigma. And then the statements analogous to what I said before. Again, if you have two weights which are in x plus, but they are fixed by sigma, then multiplicity of Weyl module of weight in the Weyl module, this Weyl module of G sigma is this polynomial at 1. And second is that product of this gamma tilde x, gamma y is again given by something involving multiplicity of the Weyl module of this smaller group G sigma in the tensor product. So I want to say something about how this thing could be proved. Let's see if I can find it. Oh, yes, yes. Okay, so now I want to talk about, so the proof of this, so I'll give a proof which involves modular representations. So namely, as I mentioned before, this theorem of modular representation was a motivating factor, so it was used as a support for a conjecture or modular representation. But we can go in the opposite way. Since the conjecture is now proved, we can use this conjecture and you can use the fact that conjecture is true and deduce. So I claim that you can deduce all these properties from that conjecture. And in particular, you can also deduce. You can also treat this this folding case. So let's see if I need some notation. So K is algebraic closure of prime field, P is a prime G large. And then X dominant weight of this big group, and Lx is a simple rational representation of this big group corresponding to X. And then we can consider this lattice of weights tensor real numbers, and can divide it. You can draw a number of hyperplanes, which is idea of Berma. That you can consider these hyperplanes for each coroot and each integer. There is such a hyperplane, and then you can identify the affine bar group, which now only involves roots, lots of roots, not weights, with the group generated by reflections in these hyperplanes. And then you take some dominant weight, which is not on any of this hyperplane, and inner product with the alpha 0, so that's the highest coroot. It's less than something over p squared. And then there's a theorem which has seven people contributed to it, and Andersen, Janssen, Sergel, etc. So it says that this L in the Grottering group, this modular representation is a combination of these Weyl modules, and the coefficients are given by this polynomial for the affine Weyl group, and the two elements involved they depend on X and Y, and I will not make them precise. It takes because not enough time. And Y is supposed to be in X plus and is in the orbit of X. Okay. So now let's assume for simplicity that the sigma square is 1. This will simplify my notation. And assume that X and Y are actually fixed by sigma. And then sigma will act on this Lx and also on VW, on the Lusztig module, and also on this Weyl module. And you can look at eigenspaces in both cases. And then I claim that there's some refinement of this character formula, which says that this difference of these two eigenspaces is given by a similar formula. That here have a difference of Weyl modules, but polynomial here is this polynomial with the defined using the length, this new length function, and otherwise it's the same formula. And so what I claim is this formula is actually it's a corollary of not of the formula itself, but of the proof of this formula. So because I claim this formula, when you prove it, the way you identify these two, it's functorial enough so that you can see how sigma acts on both sides, and then get this thing. And one ingredient is that this polynomial using this.
Can you push up the page?
Sorry, you don't. Yeah, sorry. this polynomial can be interpreted in terms of a trace of sigma on some stock of intersection cohomology. That's the main. That's only part that you need in addition to the proof of this formula before. And then and then from this formula you can deduce the formula that multiplicity of a weight in a Weyl module is given by one of these polynomials at 1, and it is given, as I explained in the beginning of the lecture. But the same argument applied here will give you that will give you this this property here for which describe this polynomial at 1 in terms of multiplicity in a Weyl module. So therefore you can prove this formula as a corollary of theory of modular representations. And one ingredient in a proof is a theorem of Janssen, which says that if you take suppose take Weyl module for this big group G, but the dominant weight is fixed by sigma, and take a difference of these two eigenspaces, then character of this will be the same as a Weyl module of the smaller group with the highest weight Y. So that is a very remarkable term of Janssen that is used here. So I think not. So one other, maybe I have 5 more minutes. Maybe I can. Yeah, going back to this this formula. So actually this actually one consequence of this formula is that this value of this polynomial at 1 is not only so you know this polynomial have value at 1 always positive, but in particular the value at 1 is positive. But this formula tells you that it's not only positive, but it's a result of counting number of elements in some set, because this multiplicity space has a canonical basis. That's one of the things which I proved. So the weight space, dimension of weight space is not only a dimension of a space, but it's counting number of elements in some finite set. And the same is true for individual coefficients of Q in this polynomial. And then it would be interesting to know if such a thing is true for more general elements in the Weyl groups or other Weyl groups. Okay, that's all I have to say.
Any questions for George? So the material unfolding that you talked about is from this paper you put on the archive yesterday. Is that right?
What is it? What are you saying?
The
yeah, it's in that paper, yes.
Okay. Maybe let me just post the link to that in the chat.
Can I ask a question? So what was your? So here it plays an. I mean, was that related precisely to what you were talking about, or?
No, I don't understand. What was the question?
What was your motivation for introducing this the asymptotic ring J? What was your original motivation? Was it related to what you were talking about today?
No.
Okay.
Unrelated.
Okay.
In fact, I didn't know this. So the J are defined in maybe 1985 or something, and I didn't know this connection until last week or something.
No, but the fact that that you can construct the this commutative part in the J ring, this is new. Is that what you're saying? Or
No. The fact that
that's older.
That's not true. But the fact that it's isomorphic, including basis with the spherical thing, that is new.
Yes. Okay, I understand. Thanks.
George, at the end, you were commenting on the fact that the value of the Cauchy-Lusztig polynomial at 1 counts the counts a set of canonical basis elements.
Yes.
And then you said that the same is true for an individual coefficient of a power of Q.
Yes.
Did you mean just that you have a set, like, is there any way of seeing which elements correspond to a given power of Q on the side of the canonical basis?
Yes, because I think so. So I think if I understand, this base bases have a filtration, which was considered by Rani Belinsky, which are related to this grading. So fact this. So these are the Q analog of weight multiplicities. So they explain the Q analog of weight multiplicity. They explain by some filtration, and filtration is, I think, is known to be compatible with canonical basis. That's what I'm using.
So I'm unaware of that fact, that it's canonic, that it's known to be compatible.
I think it is probably contained in one of my papers on canonical basis, I think. Oh, but anyway, so I haven't thought carefully about it, but at least the whole thing, maybe the whole thing is certainly is a counting canonical basis, the value at 1.
I'm confused about the relationship between this new theorem on folding and this old theorem of Knott that you mentioned.
Yes.
So if you said that 1, 2, and 3 held in unequal parameters, you were talking about the normal wing length dual. Oh, wait, I guess then, never mind. I guess it makes sense via that result of Jensen.
No.
It just seemed like if you're using unequal parameters that come from folding,
Yes.
then one way should get you the multiplicities in the wing length dual group, and the other one should have something to do with folding. But these are the same because of that result of Jensen you mentioned.
No, but in this business, I think the most interesting part for me is that that you get some is a proof, not a result, but a proof is more interesting, because you get some refinement of the character formula for modular representations. You get something where not only group acts, but some disconnected group acts. So you get some refinement, and it involves this polynomials with the using weight. So I think that was not known as far as I can tell.